This lesson will cover section 6-3 over law of sines and law of cosines. I'll go over a handful of problems that show you how we can use these laws to solve these Doric problems. So here's the first one. A 10-meter telephone pole casts a 17-meter shadow directly down a slope when the angle of elevation of the sun is 42 degrees. Find the theta, the angle of elevation of the ground. So they provide us a picture. A 10-meter telephone pole, they're talking about this right here. Notice the 10-meter telephone pole goes from here, point A, to point C. And the shadow that it's casting is on the slope. Here's the slope of the hill. And the 17 meters goes from here to here, C to B, and it's labeled 17 meters. The angle of elevation of the sun is 42 degrees. So from over here, they're telling us the angle of elevation is 42 degrees. Now the theta, if you notice in the pictures right here, it's asking us to find this little piece right here. So I'm going to zoom in to help you visualize a little bit better what's going on. Okay, so notice 42 degrees is this entire angle B, but this is what we're looking for. Okay, so in essence, if we were to figure out what this angle was right here, we would be able to figure out what this piece is right here because we know the total angle measurement is 42 degrees. So what I propose we do is we focus solely on this triangle, triangle ABC. Okay, so I'm going to pull this triangle out. I'm going to do my very best to provide a sketch of what you're seeing there. So I'm going to draw line segment AB, AC, and then BC. Okay, so we have angle B, angle A, angle C. And we know that we are looking for this piece right here. Okay, that's our question mark. And we are given that this is 10 degrees. I mean, not 10 degrees, 10 meters. That this is 17 meters. Okay. And, and we're given here that this is 48 degrees. All right. So we are looking for this angle, angle B. So if we look at the setup, we have an angle and a side across from one another. So that easily can help us start out using law of sines. I'm going to do sine of angle A over its corresponding side equals sine of angle B, which I don't know what it is, over its corresponding side of 10. My goal is to solve for B. So I'm going to do my cross multiplication and solve for sine B. So I know I'm going to multiply those two and divide by 17 to isolate sine B. So 10 times the sine of 48 degrees over 17. I need to solve for B, so that requires me to take the inverse of both sides. 10 times the sine of 48 degrees over 17. And when you type all of that in, make sure your calculator, again, is set to degree mode. So it's set to degree mode. Sine inverse, 10 times the sine of 48 divided by 17 if we round to the 100th place, B is approximately equal to 25.92 degrees. But you remember that our goal was not to find angle B, which is this piece right here. Our goal was to find this piece right here. But we knew that this entire angle was a total of 42 degrees. So our theta, which is what we're looking for, would just merely be 42 minus 25.92. So if I do 40 minus my previous answer, I'm going to get 14.08, rounding to the nearest hundredth again. Theta is 14.08 degrees, which is the angle of elevation of the ground. And you can't see anything I just wrote. My apologies. Okay, so 42 degrees minus 25.92, which is what we got from here, will be the 14.08. Zooming out a little here, you'll notice that we knew this whole thing was 42. We had just figured out this piece right here, which is this piece, okay? So we did 42 minus that piece to get the leftover, which is your theta. All right, let's try another problem. Here is the second problem. 100-foot vertical tower is to be erected on the side of a hill that makes a 6-degree angle with the horizontal. Find the length of each of the 2 guy wires that will be anchored 75 feet uphill and downhill from the base of the tower. So let's kind of analyze this picture. The 100-foot vertical tower, so this is our tower, so we can assume that this vertical distance is 100 feet. The 6-degree angle with the horizontal. Horizontal is slope of 0. Okay, so it's going to be represented by this dashed line. So if I use this ruler to kind of give you that picture of a horizontal, let's straighten out my paper to make it a little bit easier to see. Okay, I'm going to put it down here this way. Okay, so here's my horizontal, and they're saying that it makes a 6-degree angle with the horizontal. So what happens is it's taking the incline is dipping a little, okay, and that dip that it makes, it's 6 degrees. All right, so here's the horizontal, and the ruler is just tilting a bit to align itself with that incline, and it dipped 6 degrees. Okay, so what they want us to do is they want us to find this length of this wire and the length of this guy wire. Okay, now again, the 100 feet represents that. The 75 feet is represented by this, and this side also is 75 feet. So let's look at this. They want us to figure out the length of this and the length of this. So let's go find what this is. Well, let's draw out this triangle. I can see that that triangle is popping out there. So I'm going to come over here just below. I'm going to draw this piece right here. And I know that's 100. And then I have the guy wire. So I know this is my horizontal. Okay, so I know it has to be perpendicular completely. Okay, and it's going to come down here a little bit, but then it's going to dip slightly. So probably dips a little bit down here. So just giving myself an approximation. You don't have to be as exact as I'm being. Okay, and then we have this distance right here that we know is 75. Okay, so 75. But again, I'm going to put the horizontal here by a dashed line to prove a point. Okay, so what happened is, remember I told you that you were at a horizontal and then it dipped down. It dipped down 6 degrees, but originally if you take it with respect to the horizontal, we know that that's 90 degrees. But if you open up this 90 degrees and dip down a little further down, okay, so it opened up a little bit more, it's no longer 90 degrees, it's actually 90 degrees plus the 6 degrees that it dipped down. Okay, so this included angle is 96 degrees now. So if I label these, let's label it M, N, and O. All right, we're looking for this guy wire, and so we're looking for, you know, I shouldn't use O, and then I'm gonna put, let's use P. I'm looking for lowercase p because I'm looking for this guy wire length, and so I have a side, an angle, and a side, so I know that I can use law of cosines on this problem because I'm looking for this. So I'm going to do p squared equals the sum of squares of those two sides, minus 2 times those two numbers again, times the cosine of the angle trapped in between. And remember, if you are looking at lowercase p, you've got to end with the angle across from them. And so if we type that all into our calculator, so let's come over here and turn our calculator back on. 100 squared plus 75 squared minus 2 times 100 times 75 cosine of 96. We're going to get this number, but we've got to remember that that number represents p squared. So I need to square root it. Okay, so I'm going to put here, don't forget to square root. To find p. So p is going to be approximately, so second square root. I'm going to arrow up to bring down the exact answer and round to the nearest hundredth place, 131.12, and those are in feet. So the first guy wire is 131 approximately. So let's now look for the other one. Okay, now the other one, the reverse happened. Okay, let's kind of draw that one out. I'm going to shift my paper up a little bit more. Okay, so I'm going to draw my horizontal. Okay, and I'm going to draw this guy wire here on this side. But this time, the guy wire will tilt it up a little bit higher from the horizontal. So my horizontal, did I do that high enough? Let's make it a little bit higher enough for emphasis. Okay, let me increase it up a little bit more. Okay, so the incline was about 6 degrees. Okay, so here's my horizontal. Okay, if I create a horizontal here, I think I should have even gone higher. That's not really giving you much of an effect, is it? Let's go a little bit higher. We're not being exact in our measurements, but I'm just trying to make sure you can see a little bit better what's going on. Okay, so here this time, this is 6 degrees. Okay, so I'm going to go back to the original just to be a little bit more accurate in our picturing. So if you notice, this is the horizontal right here. I want you to focus on this triangle right here. Okay, so instead I'm going to align it with this incline, and so when I go up, okay, it's losing its 90-degree angle. You see right here, if I align it with that dashed line, this here is 90 degrees. But if I close in on my 90 degrees, I'm making my 90 degrees smaller. By how much? By 6 degrees. So it's tilting up. So it's losing 6 degrees. Whereas on the left-hand side triangle, it was at 90 degrees and it opened up some more. It added on 6 degrees. So here we opened up to increase 6 degrees. On the second triangle, we are going to lose. Okay, so let me shift back up to my poor attempt at drawing that second triangle. So now my 90 degrees that once was, okay, has lost this piece. So instead now it's 90 minus 6. Okay, so let's call this triangle ABC. Okay, triangle A is 90 minus 6, which in this case would be 84 degrees. We are looking for this side, which is little a. Again, we do know what this angle is. Okay, when was it? Sorry. Oh, sorry. We knew what this side length was, 75. Okay, and what else did we know? Oh, we knew this here, 100. So we have a side angle and a side. So again, it's law of cosines. We're looking for a, so we'll do a squared equals the two sides that we do know. So that's 100 squared plus 75 squared minus 2 times 100 times the 75 cosine of 84. Put that in the calculator, you will square root it, and you'll end up with 118.56 feet. Okay, one more to go. Let's try out this last example. Okay, so determine the angle theta in the design of the street light shown in the picture below. So notice what's given to us. They've given us the length of this side, this piece, and this piece of the street light, and they're asking us to figure out the angle that this street light needs to be projected at, given these measurements, that is. So we noticed that what they did is they gave us a side situation. So if we need to find that middle angle, what are we going to do? So once again, it's a law of cosines problem. Let's label our, here's me doing my poor sketching again. So this, and this. So A, B, C. We know this is 2, we know this is 3, and we know this is, I'm going to put 4.5, okay? And we are looking for angle B in this situation. So find B. So if I'm looking for angle B, I have to use the formula for cosines. For cosine B equals A squared plus C squared minus B squared over 2AC. Okay, so I'm looking for this. A is this side, C is this side, and that's going to be my B. So you always add the two sides that include the angle, and I'm going to subtract by the side that's across the angle. So let's just substitute what we have labeled thus far. So we've got 3 squared plus 2 squared minus 4.5 squared over 2 times 3 times 2. Again, remember those numbers will always match those numbers. So we will put that into our calculator. Okay. Well, actually, before we put that in that calculator, let's talk about how we are solving for b. So we need to take the cosine inverse on both sides. So let me go ahead and do that before we type this entire statement and let the calculator do all the heavy lifting. Okay. And we'll once again round to the nearest hundredth. Okay. So here we go, cosine inverse. So we do second cosine. And I'm going to put the stack fraction and then do 3 squared plus 2 squared minus 4.5 squared. And I'm dividing by 2, 3, 2. Now let's close it off. And our angle is 127.17 degrees. And that's it. So notice that the problems specifically need you to look for those triangles that are embedded within the application problem sketch, or if you were having to sketch it yourself, and then solve just like you always have been doing. Thanks for watching.